Hello. So I am discussing the digital image processing and imaging fundamentals here, which is the second chapter. I'll not be completing the full chapter here, though the contents of the chapter will be consisting of the human visual system, light and electromagnetic spectrum, image representation, image sensing, image acquisition, sampling, quantization, and resolution. But today I'll be completing only up to image sensing and acquisition part. Going ahead, uh, first, let's go to the human visual system. So, this human visual system is the best vision model that we have, and you have studied that to some extent in your class 9 and 11 physics, where we had the photo of the eye. And the main thing is that here we would be discussing how images are formed in the eye, and that you have already done in your school level. Still, to just discuss it over way, uh, overview of that, you can see this is the very popular eye image where you are having the cornea eye dish controlling the muscles of how light goes in, and you have this retina, and there you have a blind spot connected to the optical nerves. And here this whole thing is covered with the things called rods and cones. Rods are around 75 to 150 million, and cones are 6 to 7 million. Now these are throughout the retina, and your image that we receive falls on the retina. The cones are concentrated on uh, the different parts of the fovea and are very sensitive to color, whereas roads are more spread out and they are more in numbers, but their sensitivity is in low level. So we have less number of cones and more number of roads, but the roads are having low level sensitivity, whereas cones are sensitivity to color. So based on this, the images are handled by the eyes and sent via the optical nerve to our brain to sense it. But whatever we do here is totally analog. So, if we go to this particular popular image of image formation of eye, you can see here that the muscles of the eye can contract here using the addition of the things, and the image is formed at the back of the retina using the rods and cones. And this is a very popular image which you have found in books. So, not going much into that, we are going to the next part is the brightness and adaptation. Now, the eyes through which we see adapt based on analog systems, and we have some issues with brightness and adaptation. So whatever happens digitally is not the same what happens here. Here we have some part of inertia, and how the we do a lot of relative sensing and adaptation based on brightness. We have something called the perceived intensity, where the light intensities and nearby things are related to some extent to them. So here, to give you example, let's go to this. These are popular Mac bands. So here, if you see, we are having the different gray levels. By gray levels, which we discussed in the initial class, is that we have zero as white and your black as sorry, zero as black and white as 255, if you consider 256 levels, that is 2 to the power 8. And here you can see it appears like there are lines here. To show you an experiment, I'm going to my MATLAB screen, where I'll show you a brief example, where if you can see my screen, mm, you can see here that we have a MATLAB program here, and what we have is that we have a program where we have this set of ones and generated multiplied by 50. Then we have uh, similar things coming for 0, 50, 100, 150, 200, 250. So we generate mag bands, and these mag bands you see are being generated, and they have the intensity variation as under. So you have intensity which is a 0, 50, 100, 150, 200, 250, like this. We have the mag band variation. But actually, if you see the mm, thing here is that this is the actual intensity which we got, but this is the perceived intensity. You can see the difference between perceived and actual intensity. We have a problem that these changes, that these lines that you can see here in the Mach bands are actually our visual uh, perception is coming in this way, where digitally it is in this particular discretized form. So this thing is one of the common problem. And when we have 0 to 255, we have this. As we go on, you see here in this particular uh, uh, thing, you have this gray level being constant, whereas the relative gray level is appears to be more because of this simultaneous contrast between this being all black and this being more gray. Say for example, this particular intensity, say, is having a level of, say, something like 50. So if we have a level of 50, so this 0 to 50 whatever is relative. Similarly, we have, say, 20 to 50, and when we go ahead, say, 100 to 50, the ratios are different. So based on our relative perception, this simultaneous contrast appears to be different because of the background. Whereas if you see programmatically, the center intensities are all same. So there may be a lot of illusions. I'm avoiding these visual illusions and coming to the electromagnetic spectrum. Now, this also is a part of your physics that you have studied in your class 9 and 10, and you are very much aware of the electromagnetic spectrum, whether it is gamma rays, X rays, UV, infrared, the visible spectrum, and radio waves. In all of these, because it is electromagnetic spectrum, the speed of light is constant. The speed of light is 3 into 10 to the power 8, which is constant. And with that, this electromagnetic signal of 3 into 10 to the power 8, we have the lambda changing, due to which the different frequencies change. And based on that, we are having the different spectrum visions. We normally discuss the visual spectrum, and you can see different colors. And as I told in my previous class, we can form the different colors based on the different signals here. If you see this MATLAB program, where we have, say, zeros and ones forming the different signals, you see, initially we consider zeros, and then we consider ones, and then we do the combination. R0, G0, B0 makes black. R1, G1, B1 makes white, means all ones are white, all zeros are black. Along with that, what we can do in the channels, if I make red equal to 1 and green and blue equal to 0, I get the red color. Red equal to 0, green equal to 1, and blue equal to 0, I get green color. And R equal to red is equal to 0, G green equal to blue, green equal to 0, and blue equal to 1 gives me blue. And once we go after this primary set of colors, if we make two of them one at a time, like R0 with G and B equal to 1, I get cyan. With R1 and G1 and B equal to 0, I get yellow. And for R1 and G0 and B1, I get magenta. CYM. If you remember, these are the three colors which we use in our printers. They are considered the secondary color which generate images which appears to be RGB. Just to show you, this is how the things are: black, red, green, blue. So black and white are the all zeros and all ones. Here only red, only green, only blue. Here everything except red, everything except blue, and everything except yellow, green is generating this set of colors. Next, if we uh, go after the electromagnetic spectrum, we have the reflected light. So this primary and secondary colors together forms what we see in the screen. Say for example, white light comes in this and falls on this object, and all colors are absorbed, and we have the green light coming out. So we have the green being reflected. So same thing is for all wavelengths, and this goes on. Now, coming to the sampling, quantization, and resolution, this is the discretization process, whether it is spatial domain or time domain, or the amplitude or the intensity level. for one dimension and two dimension. Here I'll be initially discussing the image sensing and representation part, and we'll be following it up with sampling and quantization and resolution. Now, to give you an example, uh, somebody may have a 2 megapixel camera, somebody may be having 20 megapixel camera. But the thing is that we can focus the whole camera onto a door. Now, when I focus the whole door with my camera and take a picture with 2 megapixel resolution, the whole door is being covered by 2 megapixels of uh, data. Whereas the same thing if I do with a 20 megapixel, the same door, the size of which doesn't change, but we have 20 megapixels representing this particular door. Now, when we have this kind of condition, what we can do here is that in one case, if we zoom in and the things do not break up and we don't have any issue with the picture, whereas the one where we say if we zoom in and it breaks up means it is having low resolution. So it is just that we are representing the same image with more number of pixels and less number of pixels. And moreover, you might be seeing that you might be having a DSLR of 16 megapixel, and you might be having a mobile camera with 32 megapixel camera. Now, the image quality of this 32 megapixel camera is no way similar to the 16 megapixel good quality image coming from a DSLR. So you might be thinking why I am having so many megapixel image. So megapixel is nothing but a hoax. But when you have this sensing device or the CCD, the size of the CCD is more in case of the DSLR, and more light is approximated to generate each and every pixel. Whereas the same is not true for the mobile cameras where the miniaturization is a thing, and as you have miniaturization, so you have the size of CCD very small. Moreover, these days you have artificial intelligence generating a lot of data. You have triple camera, quadruple camera, and so on. So multiple cameras at different level of focusing with different image processing algorithms are generating uh, different images. Some of the images are rendered using artificial intelligence and pixel-wise interpolation, blocking. So high-end DSP techniques or image processing techniques are also applied for this kind of stuff. So going ahead, this is the image representation. We have 0 to 255 from black to white, and these are the different location, and each location is 1 pixel. In case you are discussing with grayscale, once you go for colored images, each of them is represented with uh, 3 channels. So if each is 8 bit and each is gray level, so the set of 3 gray levels, so 3 into 8 is 24 bit. So you might be thinking, what is this 24-bit thing? So if I open my MS Paint, which is a very popular tool which all Word or Mac has, if you see there is a save as option. So here if you zoom in, you see there is a option that you are having 24-bit bitmap or BMP or file. So this 24-bit map is nothing but we are having this 24 bits of colors, which is 8-bit into 3 for the 3 channels. Going ahead, this is the image acquisition part. Now, whether we have any particular image or scene, it is once we illuminate the scene with the illumination or energy, and whatever energy is falling in it is reflected to the CCD system, and the approximate internal image is there, and then we have the image being generated, whether it is X-rays, ultrasound, or whether it is an MRI scan or CT scan, we are having this kind of system. This image sensing that we have maybe um, using a single image sensor like this one, or it may be a line, like in case of scanner we have a single line sensor, so it is an array sensor or line of image sensors, or we can have a bigger array, 2 dimension array. So this is a single element image sensing. This is a single row wise or column wise image sensing. We have line sensors, or we can have array image sensors like the CCD example of the digital cameras as I discussed. So these collections of the center sensors are generated to capture the different images. This line of image sensors is very popular for scanners, and image sensor are there which form these particular things when coming in a line or coming in row and column format. So when it is one dimension, here the whole based on linear movement and the strip being here, the image area is scanned and the image is coming up. In case you want some three-dimensional images, so you can have them using this uh, MRI scan where continuously the 3D object is there and continuously it is imaged from this particular portion circularly, and we have cross-sectional images which form the 3D object in a single stage. When we go to image sampling and quantization, what happens here is that we have a digital sensor which can only measure a limited amount of light, and these samples. So if I have one particular image here, here we do the sampling in this way, and we do the quantization by converting the continuous and long value. So here what we have discrete amplitude and discrete time or discrete spatial domain signal. So it is discretized in both time spatial domain or time domain as well as amplitude, based on which we have the discrete values coming up. So this is the image thing. We sample it in this way. So as the sampling goes on, we have the different amplitude of different gray levels, and this particular image is digitized or approximated in this way. So this I'll continue this in the next lecture. So thank you for now. I'm uh, closing here, and in the next lecture I'll be discussing the things in details. So I'm stopping here, and the rest of the lecture I'll cover up in the next class. So thank you. Here to summarize, we have looked into the human visual system, we have looked into light and electromagnetic spectrum, and we have looked into image representation, image sensing to some extent. The sampling coordination resolution part is left, which I'll be discussing in details in my next lecture. So closing up, uh, I would like to stop here. Thank you.